right? This is 4.1.3 kinematics. First, we're going to start by defining velocity and acceleration mathematically. So velocity is defined as the rate of change of displacement. So we write that down mathematically. Rate of change means ds dt. Now if something is linear, then you can just take that as delta s over delta t. So it's the rate of change of displacement. Acceleration is defined as the rate of change of velocity. So A is equal to dv dt. It's also the second derivative of displacement. And again, if it's linear, we can just do delta v over delta t. Now, a value that we need to always keep in mind is the acceleration due to gravity. If things fall or move vertically, then acceleration due to gravity will always be pointing in the downwards direction and will always have a value of 9.81 meters per second squared near the surface of the Earth. So acceleration due to gravity G equals to 9.81 meters per second squared. So if your object is falling or moving vertically, so this could be up or down, take your acceleration as equal to g. So for example, if we throw something in the air, it's not accelerating upwards. It might be moving upwards initially, but it's constantly accelerating downwards. Hence why when you throw something in the air, instead of speeding up as it goes up, it slows down. Then at some point it stops, and then it falls back down again. And as it falls back down, it starts to speed up in the downward direction. So it's accelerating downwards the entire time. And a negative acceleration, so if acceleration is not in the same direction as velocity, it causes the magnitude of velocity to decrease. Acceleration only causes magnitude of velocity to increase if they're acting in the same direction. So, next, you need to memorize these equations of motion for constant acceleration. So these equations only apply if acceleration is constant. If acceleration is not constant, you cannot use these equations. So equations of motion for constant acceleration. V equals to u plus at. V squared equals to u squared plus 2as. S equals to ut plus a half at squared. S equals to vt minus a half at squared. And then S is equal to V plus U over 2 times T. Put a box around these equations. You need to learn these. And then we'll define all the terms. So V is the final velocity measured in meters per second. U is initial velocity measured in meters per second. S is displacement measured in meters. A is acceleration measured in meters per second squared. And T is time measured in seconds. Now, to use these equations, when you start with the problem in front of you, write down VUSAT. So step 1 is to write down VUSAT. Step 2 is to write down known values from the question underneath each letter. So the question will give you some of these values. So write down known values underneath. So for example, say if our question said an object starts at rest. Starts at rest means initial velocity is 0. So the question's told us that in words. And it ends up with a final velocity of 10 meters per second after moving 1 meters. So we know that V is 10 and S is 1. And the question then asks you to calculate the acceleration. So we want to find acceleration, and those 3 are the values that we know. So third step is decide what you want to find out. So in deciding, we're going to decide we're going to find acceleration. But we don't know acceleration. So finally, we're going to choose an equation where only one thing is unknown, and that one thing is the one we want to find. So choose equation with only one unknown. So in this situation, we have 2 unknowns, which is acceleration and time. We're interested in working out acceleration. We're not interested in working out time. So out of those equations, we can't use V equals to U plus AT, because that contains time and A. We can't use S equals to UT plus half AT squared, because it contains time. We can't use VT minus a half AT squared, because that contains time. So we're going to use V squared equals to U squared plus 2AS, because that only has one unknown, which is A. So that will be the equation that we're going to use in this example. Let's do an example question. So we throw a ball upwards. At 6.0 meters per second. So A, how long does it take to reach the top? And B, how far up does it go? Pause the video here to attempt the question and play the video to see the solutions. Right, let me solve it. Right, to solve this problem, for part A, we know that when the ball reaches the top of the throw, its maximum height, it's going to stop before it turns around and falls back down. So if it stops for a moment, it means that at the peak of its height, its final velocity is going to be 0. So we'll use V equals to U plus AT. So we've got 0 for U, for V, equals to 6 for U, plus A times T. Now, there's a caveat here. We said use A as equal to G. But we're talking about up and down right now. So one side is positive, one side is negative. The rule I always go for is imagine everything lives on a graph. So up is always positive, down is always negative. So for A, it's going to be minus 9.8 T. And then we rearrange. So we've got 9.8 T is equal to 6. So T is equal to 6 over 9.8. And that equals to about 0.6 seconds. Then, part B. Part B asks for how high does it go. So you can solve this in multiple ways. Now that we have a value from part A, we can actually use that to work it out. But my recommendation is, if it's possible not to use a value that you calculated, because you might have calculated it wrong, is try to use a way that doesn't rely on the value that you just calculated. So for that, we can do V squared equals to U squared plus 2AS. V squared is just 0 squared, which is 0. U squared is 6 squared, so that's 36. Plus 2 times A times S. Now A, again, was negative. So minus 2 times 9.8 times by S. And then we can rearrange this. So bring the negative term to the other side. 2 times 9.8 times S equals to 36. So S is equal to 36 over 2 times 9.8. So that's roughly equal to about 1.8 meters. Okay, start a new page. Next, we'll talk about graphs. So we start with the definition of velocity. Velocity is the rate of change of displacement. We put a box around that statement. That's a definition you need to learn. Now, rate always means per unit time. Per means to divide. So rate means divide by time. So we go back to V equals to ds dt. Now ds dt basically means gradient of an ST graph. It could be a straight line. It could be a curve. It just means a gradient of. Now, if you have a curve, you normally won't be given a function in physics, so you'll have to draw a tangent at the point which you're interested in, then work out the gradient of that tangent. Next, we'll define velocity again. So velocity, sorry, acceleration. We've done velocity just now. Or we'll do some examples first. And then we'll move on to acceleration. So ST, ST, ST. So if we have a straight line, this means that velocity is 0 because there is no gradient. So therefore, this is stationary. If we have a straight line like this, this means that there's constant positive velocity. It means that the object is moving, but it's neither slowing down nor speeding up. If we have a straight line like this, this is a constant negative velocity because the gradient is negative. If we have a curve, like so, this is accelerating in the positive direction. And for this one, it's still accelerating, but in a negative direction. Now, the next two, there is still acceleration. Typically, you would call this deceleration. But it's acceleration in the opposite direction to velocity. It's for both of these cases. So acceleration in opposite direction to velocity, which some people call as deceleration, so it's slowing down. Okay, start a new page. Now let's define acceleration. So acceleration is the rate of change of velocity. So A is equal to dv dt, which means it's the gradient of a vt graph So a constant line like this means no acceleration, constant velocity. This is accelerating, same direction as velocity, or positive direction. And then here we can have accelerating in the negative direction. Which initially does cause this object to slow down because its magnitude of velocity is decreasing. But once it crosses that x-axis and goes into negative velocities, after that point, it starts to act as an acceleration because it speeds up the object beyond that point. So if you were to extrapolate that graph beyond the x-axis to go into the negative velocities as a straight line that continues, then the object is speeding up. Next, we'll look at the area under a VT graph. So the area underneath this is equal to displacement. Now typically, again, you won't be provided with the function of the graph. So instead, what you do is you split it into geometric objects that you are able to work out the area of. For example, triangles, rectangles, trapeziums. So in this situation, split it into three shapes, read the numbers off the graph, and then calculate the area of these three. Now, area is given by the integral. So v is a function of time, dt, from 0 to some value t. You're not expected to use calculus at A-level physics. However, in some situations, it becomes beneficial to be able to use numerical methods. For example, the trapezium rule. Now we'll look at a common graph, which is throwing a ball up. Then catching it. So if we throw a ball upwards, the moment the ball leaves your hand at t equals to 0, the ball has a large positive velocity because it's moving upwards. When the ball reaches the top its velocity becomes 0. Meanwhile, the acceleration was negative and it was constant, which means we're going to have a straight line graph. After the ball reaches the top and it's stopped, it's got 0 velocity, it then accelerates downwards, or continues to accelerate downwards, and its magnitude of velocity increases in the negative direction. Again, with constant accelerations, we carry on as a straight line. And when you catch it, we assume that the instant you catch it, its velocity drops to 0. Now, the magnitude of these velocities we'll call Vmax and negative Vmax. They're the same. So the velocity it had as it left your hand going up is the same velocity the moment you catch it, but going down. The area of this region here moving upwards is the same area as this region down here moving downwards. So if you've got the upwards area, which gives you the displacement upwards, minus the downwards area, which gives you displacement downwards, if you add them together, a positive displacement upwards minus a displacement downwards gives you overall 0 displacement. That's the end of 4.1.3.